Welcome back to the deep dive. Today we're stripping away the sleek bodywork, the sponsor stickers, and all those roaring engines to look at what actually wins races.
Right, because it rarely is what people think it is.
Exactly. Hint for you listening, it isn't just about who has the heaviest right foot or the biggest ego, honestly.
No, it really isn't. In modern racing, victory is usually decided long before the car even hits the track.
Which sounds crazy, but it's true.
We're talking about that razor-thin margin where physics meets engineering.
Specifically this concept of marginal gains. You know that whole philosophy where if you improve everything by just 1%.
Right, the Sir Dave Brailsford idea.
Yes, exactly. If you tweak your sleep, your nutrition, the aerodynamics, even the tire pressure by 1%, those tiny gains aggregate into a massive competitive advantage.
They do. Because in high-stakes environments, whether that's the Olympics or aerospace or the racetrack, you don't usually find a silver bullet.
There's no magical button that makes you twice as fast overnight.
Exactly. You find 100 tiny things that make you a fraction of a second faster.
But here is the catch, and really this is the core of our deep dive today. You can't improve those tiny things if you can't see them.
Right.
Basically, you can't optimize what you can't measure.
That is the absolute mantra of engineering. If you are guessing, you are losing.
So we have a really fascinating stack of sources today that tells a specific story about this battle against the unknown.
It's a great case study.
It is. It involves Interface, which is this heavyweight global leader in force measurement solutions. And they partnered with a group of underdog engineers who might just be the future of the automotive industry. Gopher Motorsports.
Yes, the Formula SAE team from the University of Minnesota.
Right.
And I'm really glad you called them engineers, by the way, not just drivers or mechanics. Because what they are doing is serious professional-grade structural analysis.
Well, it's wild. It really is a masterclass in the difference between simulating performance, which is basically guessing what a car will do based on math, and hope.
Mostly hope sometimes.
Right, the difference between that and actually measuring it to know the cold, hard truth.
And that truth is often found in the invisible forces pushing and pulling on the car that your eye just cannot see.
So let's set the scene for you. Gopher Motorsports. For anyone listening who might be thinking this is just a collegiate car club where people hang out in a garage, drink soda, and talk about mufflers, you need to correct that assumption right now.
Oh yeah, far from it. Formula SAE is a brutal global design competition. It is arguably one of the most rigorous engineering challenges a student can face anywhere.
Because they don't just build one car, right?
No, these teams design, build, and compete with 2 race cars every single year.
2? That just seems excessive.
It's incredibly ambitious. They build 1 internal combustion vehicle and 1 electric vehicle.
Right.
It's a massive undertaking.
Wow.
And the competition structure itself is fascinating because it mimics the actual automotive industry. It is not just a race.
Right, I was reading the source material on the judging criteria. They aren't just judged on who crosses the finish line first.
Not at all. Speed is critical, obviously. But they are evaluated on engineering design, manufacturing, quality cost analysis, and business logic.
Business logic, too.
Yes, they have to stand in front of a panel of judges who are often industry pros from places like Ford or GM or SpaceX.
Oh, no pressure.
Right, and they have to defend every single bolt on that car.
So you can't just say, hey, we put this wing on because it looks cool?
Oh, you would get laughed out of the room instantly. You have to say, we designed this wing to generate exactly this many pounds of downforce at 40 miles per hour, costing this many dollars to manufacture.
To improve cornering speed by Z%?
Exactly. It's an engineering defense.
It sounds a lot more like a doctoral thesis defense than a fun track day.
It really is. And to survive that kind of defense, you need data. You need absolute proofs. You cannot rely on intuition.
Which brings us to the specific engineering headache Gopher Motorsports faced in our sources today. The suspension system.
The heart of the handling.
Yeah, let's pause and unpack this for everyone listening, because I think most people have a basic idea of what suspension is.
Right, the springs.
Yeah, the springs that stop your coffee from spilling when you hit a pothole on the highway.
Sure, on a road car, comfort is king. You want to isolate the passenger from the road. But in racing, suspension has a totally different job description. Its primary role is managing weight transfer to maximize the contact patch.
The contact patch, that's the tiny square of rubber where the tire actually touches the road.
Exactly. It's about the size of a human hand.
That's it.
That is it. That small patch is the only thing connecting a moving vehicle to the earth. Everything you do, acceleration, braking, turning, it all happens through that patch.
So if the suspension is sloppy or if the car leans too much, that patch lifts up.
Or it just gets uneven pressure. Imagine you are taking a sharp corner at 60 miles per hour. Physics wants to throw the entire weight of the car to the outside wheels.
Right.
If you brake hard, the weight slams forward. If you hit the gas, it shifts back to the rear.
It's like this chaotic dance. The weight is sloshing around constantly.
It is violent.
Yeah.
And the suspension's job is to manage that shifting mass, so those 4 tiny patches of rubber stay glued to the asphalt with consistent pressure.
Because if you lose that pressure,
You lose grip. And if you lose grip, you spin out.
or at the very least, you just go slower because the driver doesn't trust the car.
Precisely. Optimized suspension equals increased tire grip. Increased grip equals faster, more stable laps.
But here is the gap identified in the source material. Designing this system is incredibly difficult because suspension linkages, the metal bars connecting the wheels to the chassis, they are subjected to really complex multi-directional forces.
And historically, knowing what those forces actually were was a total black box problem.
Meaning they couldn't see inside this system?
Meaning they had to guess. Before advanced sensors became accessible, teams relied on 2 things: computer simulations, which are purely theoretical, and driver feedback.
Right. The driver comes in after a lap and says, it feels a little loose in turn 4.
Or I'm getting understeer on entry.
Yeah, it feels loose. That's so subjective.
It's incredibly subjective. One driver's loose is another driver's agile.
Yeah.
And simulations are great, but they usually assume a steady state. They assume the track is a perfectly flat plane, the tires are perfect spheres, and the air is perfectly still.
Which is never true. The real world is messy. Tracks have bumps and vibrations and wind gusts.
Exactly. So Gopher Motorsports had this aha moment. They realized that if they wanted to win, and if they wanted to survive those design judges, they needed to stop guessing.
They had to get real numbers.
They needed to measure the actual forces traveling through the suspension while the car was literally screaming around the track.
But this is where the engineering reality hits, right? You can't just tape a bathroom scale to the axle.
No, definitely not.
You can't throw standard, bulky lab equipment onto a race car.
You have 2 massive constraints. First is weight. In Formula SAE, every single gram counts. You cannot add heavy testing gear because a heavy car is a slow car.
Makes sense.
And second is durability. The suspension area is a very hostile environment. It's vibrating, it's hot. There's dirt, oil, brake, dust, stones flying up everywhere.
So they needed something rugged, tiny, and incredibly precise, which is where the partnership with Interface comes in.
Right. This is where the story pivots from the problem to the solution. Gopher Motorsports worked with Interface and their regional partner, Minnesota Measurement Engineering.
Okay.
And they integrated a very specific hardware solution into their Gopher 23C vehicle.
I just love that name, Gopher 23C. It sounds like a droid from Star Wars.
It really does.
But let's get technical for a second here. What exactly did they install? Because Interface makes a lot of different sensors.
They implemented 12 Interface mini-load cells. Specifically, they used 10 of the SSM-sealed S-type load cells and 2 of the SMS-type load cells.
Okay, for the listener who isn't a metrology nerd, what is an S-type load cell? How does it actually work in plain English?
Picture a solid piece of metal machined to look like the letter S. When you pull on the top and bottom of that S, the metal flexes slightly. It deforms just a tiny, tiny bit.
Okay, so it stretches.
Yes. And bonded to that metal are strain gauges. These are tiny electrical resistors that change their resistance when they are stretched or compressed.
I see.
By measuring that change in electricity, you can calculate exactly, and I mean down to the fraction, exactly how much force is pulling on the S.
So it literally converts physical stress into an electrical signal.
Precisely. And the SSM part is crucial here. The sealed aspect. Remember that hostile environment we talked about with the rocks and oil?
Right.
These cells are environmentally sealed to protect those internal gauges from moisture, dust, and grime.
That seems pretty vital. If you're running on a track that might be damp or dirty, you don't want your data going haywire just because a speck of dust got in.
Oh, it's non-negotiable. If moisture gets into a strain gauge, your data is garbage. You end up chasing phantom problems that don't even exist.
And the mini part of the name, these things are really small.
They have to be to fit inside the suspension linkage. But don't let the size fool you. These specific models were rated at a 1,000 pounds force capacity.
Wow, so a sensor that fits in the palm of your hand is holding back half a ton of force?
And measuring it with high fidelity. It's really a marvel of modern manufacturing.
The implementation here is what I find so cool. They mounted these things in line. Can you explain what that means for the car's architecture? Because reading the source, that sounded incredibly risky.
It is risky if you don't trust the hardware. Inline means the sensor actually becomes a structural part of the car itself.
Okay.
They cut the suspension rods, the push rods and tie rods, and threaded the sensor right into the middle of them.
So the physical force has to travel through the sensor to get from the wheel to the chassis.
Exactly. There is no bypass. If that sensor fails structurally, the suspension collapses. The wheel could detach or fold completely under.
Talk about putting your money where your mouth is. That is a high-stakes engineering choice. They are betting the entire car on the durability of these interface sensors.
They are. But it solves the problem we talked about earlier. By putting the sensor in the direct line of fire, you aren't estimating the force anymore. You aren't inferring it from some secondary location.
You're capturing the reality.
You're capturing the exact reality of the load path. You're basically measuring the heartbeat of the suspension.
So they build the car, they install these 12 mini load cells, they hit the track, and this is where the workflow shifts from just building to actually tuning.
Right, they enter the data collection phase. And this is where the magic happens. They ran the car through very specific scenarios. Heavy braking, cornering at maximum G-forces, acceleration sprints, and navigating track bumps.
And what they found from the data was that reality is much more complex than their simulations. The sources highlight something called off-axis loading.
Yes, this is a huge concept in mechanical engineering, and it's something simulations often really struggle with.
Break that down for us. Why is off-axis loading such a massive headache?
Okay, let's use an analogy. Imagine you are holding an empty soda can. If you squeeze it perfectly from the top and bottom, just straight down, that's axial loading. It's incredibly strong. You can actually stand on an empty soda can if your balance is perfect.
Right, because the walls of the can hold the weight straight down.
Exactly. But if someone just taps the side of the can with their finger while you are standing on it, that side load is an off-axis load.
Oh, and the can crumples instantly.
Instantly. Because it's not designed to take force from that direction.
Ah, I see.
In a suspension system, you design the metal rods to take pushing and pulling axial loads. But because the car is twisting and the tires are scrubbing against the asphalt and the whole chassis is flexing, you get these weird side loads, these off-axis forces.
And I assume those wobbles or side loads are what snap parts when you least expect it.
They're the silent killers of race cars. They cause fatigue. They cause hysteresis, where the metal bends but doesn't bounce back perfectly.
And without sensors, these forces are completely invisible.
You wouldn't know they are there until the part breaks on the track.
So with these interface load cells, Gopher Motorsports could actually see these invisible forces mapping out on a graph in real time.
Yes, they could validate their design assumptions. They could look at the data and say, hey, the computer model said we'd have 500 pounds of force on the front left toe link, but the sensor is screaming that it's actually 700 pounds.
That is a terrifying discrepancy if you didn't know about it.
It is the difference between finishing the race and a catastrophic failure on lap 10.
Or I guess it could go the other way, right? Like, we built this part to hold 1,000 pounds, but it never sees more than 200, and we made it way too heavy.
Exactly. And that's the marginal gain we started talking about. If you know it's overbuilt, you can shave off metal. You make the car lighter. A lighter car accelerates faster and brakes shorter.
Wow.
They fine-tuned the suspension geometry based on this real-world data to reduce those stress concentrations.
And the result wasn't just a safer car, it was actually a faster one.
The source material is very clear on this outcome. The data directly influenced grip handling stability and lap consistency. When the driver pushes the car hard, it behaves predictably because the engineers remove the structural surprises.
It builds a ton of confidence.
And a confident driver is a fast driver. If you're worried the wheel's going to fall off, you're going to lift your foot off the gas.
Always. It's amazing how it all connects. You have a tiny sensor measuring a generic force, and that data point ripples up to become a split-second difference in a lap time, which eventually becomes a trophy on the shelf.
That is the core value proposition here. Reliability and safety come from truly knowing how forces travel through a mechanical system. You move from theoretical engineering to measurable engineering.
Now I want to zoom out a bit. We've been geeking out on race cars for a while, which is fun, but I'm guessing most of our listeners aren't currently building Formula SAE vehicles in their home garages.
Fair point, though it would be a pretty cool hobby to have.
It really would. But how does this connect to the bigger picture for you listening? Because the sources explicitly mention that this isn't just about racing, this is actually about Industry 4.0.
It absolutely is. The principles Gopher Motorsports use sensor integration, real-time data collection feedback loops. They are the exact same principles driving the modern smart factory.
Industry 4.0, that's the whole automation and data exchange trend, right? Basically the Internet of Things, but for massive factories.
Yes. Think about a robotic arm in a car factory in Detroit, or maybe a tech plant in Silicon Valley. It's welding a door frame or assembling a delicate smartphone screen. How does it know if it's applying the right amount of pressure?
Right. It doesn't have feelings. It doesn't have a nervous system.
Exactly. It needs sensors. It uses interface sensors. The source notes that these exact same load cells, torque transducers, and multi-axis sensors are standard for component validation, brake testing, and pedal force testing across the entire automotive industry.
So the tech in this student race car is literally the exact same tech ensuring my minivan's brakes actually work when I press the pedal.
Precisely. And it goes even further than that. In modern manufacturing, they use this technology for predictive maintenance.
How does that work in practice?
Oh, let's say you have a massive machine drilling holes into heavy engine blocks. If the drill bit starts to get dull, it takes more force to punch through the metal, right?
Yeah.
A human standing 10 feet away might not notice that subtle change.
Yeah.
But a load cell detects that spike in force instantly.
And it tells the system, hey, change the drill bit before you ruin the engine block or break the whole machine.
Exactly. It is quality control happening at the speed of light. Just like the race team uses data to optimize the lap gate, a factory uses data to optimize production. It prevents downtime and saves millions of dollars.
There is another layer here that I found really compelling in the sources, and that's the human element, the education aspect of all this.
This is huge. We have to remember Gopher Motorsports is a student team. They are at the University of Minnesota. Their primary goal there is to learn.
But they aren't just learning from a textbook in a lecture hall, they're doing real applied engineering.
By using this pro-level gear, these interface load cells, they are gaining hands-on experience with the exact tools the actual industry uses today. They aren't training on toys.
It's one thing to read about load cells on a slide. It's totally different to solder them into a wiring harness, calibrate them, interpret all that noisy data, filter out the engine vibrations, and then redesign a physical part based on what you found.
That creates a massive skill advantage for them. We talk about the skill gap in engineering and manufacturing constantly. Companies are desperate for people who don't just know the theory, but know how to wrestle with real messy data.
So these students are graduating already fluent in the language of modern manufacturing.
They are completely industry ready. They understand deep down that you can't optimize what you don't measure. They've lived the frustration of getting bad data and the absolute joy of solving it. You just can't teach that in a PowerPoint presentation.
It's such a great example of how a partnership like this between a company like Interface and a university isn't just a corporate donation, it's a real investment in the future workforce.
Absolutely. It bridges the gap between the academic bubble and the hard realities of physics and business. It prepares them for those intense boardroom defenses we talked about earlier.
So let's bring it all home. We started this deep dive with a group of students simply wanting to make a car go faster around a track.
And to do that, they had to stop guessing. They moved away from relying solely on subjective driver feel or computer models that couldn't account for every single bump in the road.
They implemented high-precision interface mini-load cells directly into the suspension linkages, which was a bold move that basically made the sensors part of the car's skeleton.
Which gave them the ground truth, the hard numbers on the actual forces at play, revealing those invisible off-axis loads that could have caused a failure or just inefficiency.
And having that data let them tune the car to win, validating their designs and cutting unnecessary weight,
while simultaneously teaching them the very skills they need to run the automated factories and engineering firms of tomorrow.
It really underlines that universal principle we keep coming back to. Performance improvement, whether you're in a race car, a factory, or honestly even in your own life, begins with accurate measurement.
Data is the flashlight in the dark room. Without it, you're just stumbling around hoping you don't stub your toe.
Here is where I want to leave us today. It's a bit of a provocative thought for you to chew on after listening. We talked a lot about how the driver's feel used to be the gold standard, the car feels loose, and now we are replacing or at least heavily augmenting that feel with hard data from load cells.
Right. The digital twin is becoming much more accurate than the human sensation.
So as we get better and better at measuring these intangible things, are we entering an era where intuition becomes obsolete? Or does the definition of skill just shift?
That is the big question, isn't it?
Like, is the new expert the person who can feel the road through the steering wheel? Or is the new expert the person who knows which data point actually matters in a massive sea of information, because you can have all the sensors in the world, but if you don't know what question to ask them, you're just staring blindly at a spreadsheet.
Interpretation is the new intuition. Data doesn't make decisions, people do. The sensors just give you much better eyes.
It's definitely something to think about next time you're driving and you feel like something is off with your car. Maybe you're right. Or maybe you just need a load cell, to tell you the truth.
I would always trust a load cell.
That's it for this deep dive into Gopher Motorsports and the world of precision measurement. Thanks for listening.
See you next time.